morning, friends. So today, in this lecture, 1 hour of lecture, I am going to talk about how to model various transmission line in power systems. Coming to the classifications of transmission line, a transmission line has classified into three models: short, medium, and long transmission line. How to classify these short, medium, and long transmission line in the sense? Short transmission line is a line where the distance of the transmission line is 50 km and the working voltage is the range of 20 kV. So what I can say is, in a short transmission line, the line which is less than 50 km and the working voltage, if it is line to line, I'm saying 20 kV, then it is coming under the model of short transmission line. The next one is a medium transmission line. In medium transmission line, we have between 20 to 100 kV. We can say that it is a medium transmission line, and the line length is up to 150 km. 50 to 150 km, we can say it as medium transmission line. The next type of model is called as a long transmission line, where the working voltage is more than 100 kV and the line length is more than 150 km. These are the various types of classifications of a transmission line based on the model. Okay. So how it is making the difference in the sense, in short transmission line, there are three parameters are there in transmission line. You know that: resistance, inductance, and capacitance. Among these three parameters, how we are going to assume, like RLC, whether it is going to be lumped in nature or distributed in nature. Practically speaking, all these three are in distributed way, but here what we are considering is, in short transmission line, we are neglecting the effect of capacitance. Why we are neglecting the effect of capacitance means, in short transmission line, the dominance of capacitance when compared to resistance and inductance is very less. Okay, that is the reason we have to omit the effect in the short transmission line. Coming to the medium transmission line, here we are going to consider all the three parameters: resistance, inductance, and capacitance. But all the three are lumped parameters. Instead of distributed in nature, we consider it as a lumped parameter. In long transmission line, here also all the three parameters are considered, but the main difference is, in long transmission line, we have RLC, which are distributed, which is the same as that of the real-time system. How the real-time resistance, inductance, and capacitance are distributed, the same way we have considered. So then that way there are three model of transmission line based on the line length and working voltage. Yeah. In order to conclude all those things, in a short transmission line, if you see that, that's why I discussed about that. It is less than 100 kV and the distance is less than 50 km. Both the resistance and inductance are lumped parameters. We neglect the effect of capacitance. All these modeling, the purpose of doing this model is to find the performance of the transmission. Performance in the sense, there are two things are there. One is the efficiency, other is the voltage regulation. Even by neglecting the effect of capacitance, if we calculate the efficiency of voltage regulation in short and medium transmission, short transmission line, there is no huge change in the corresponding number which you are getting. That is why we are neglecting that. Not easy the calculation. That's it. In medium transmission line, as we discussed, 20 to 100 kV is the working voltage, and the line length is between 50 to 150 km. So that is why here also we consider all the three: resistance, inductance, and capacitance. The main thing is, all the three parameters are lumped. So if we go and see the calculation practical value with this, there is a slight mismatch between the practical value and the theoretical computation which you are doing with these assumptions. So to overcome that, we have to go for long transmission line. Long transmission line is a line where the distance is more than 150 km. In the sense, the distance between the sending end to receiving end is more than 150 km, and the working voltage is more than 100 kV. Then it is called as a long transmission line. In long transmission line, if you assume all the three parameters to be lumped in nature, so what happens means, because of that, the error which is developed in the transmission line or the performance is very more. That is why you can't able to do that. In long transmission line, there is a method called rigorous method. Using that method, we have to find the voltage regulation and efficiency. There is a three way of classifications. So performance of the transmission line. In all these three cases, as I said, there are two things we have to do. One is the voltage regulation, other one is the efficiency of the transmission line. See, here, to find the voltage regulation, the general formula which you are using in your transformer, etc., it is Vs minus Vr by Vr into 100, where Vs is the sending end voltage, Vr is the receiving end voltage. and VR is the VR divided by VR will be the corresponding voltage regulation, and the tolerance limit should be within plus or minus 5%. The voltage regulation which we considered should be within plus or minus 5%. That is the thing we have to maintain. Then coming to the transmission efficiency, this is also important. We are trying for 100% of efficiency, but practically it is not feasible to get or possible to get 100% efficiency. So in that case, what we are going to do is to find the transmission efficiency. You know the here Vs, Is, and cos phi s are the sending end parameters. Vr, Ir, and cos phi r are the receiving end parameters. So receiving end power by sending end power will give you the efficiency of the transmission line. Okay. So as much as possible, we are trying to improve the efficiency more than 90-95% by adding some of the components like fax devices, etc. So these two we are going to discuss. What is how to find the voltage regulation, how to find the transmission efficiency for different case of model. Yes. Yeah. First one is the a short transmission line. In short transmission lines, we assume that all the transmission lines are analyzed in the per phase model. That means since it is a balanced system, we assume that the system is balanced. Here we consider that all these models, when discussing all the model short, medium, and long transmission line, the line which is considered is a per phase model. So here if you see that there is a sending end voltage, VR represents the receiving end voltage. The lumped parameter, the resistance and inductive reactance are shown here. That is the total resistance, total inductive reactance. And the current which is at the sending end is Is, current at the receiving end is IR. In this case, both are equal because we neglect the effect of capacitance. There is no parallel branch or shunt branch. That is why Is is equal to IR over here. So remaining things are there. Then cos pi r is the receiving end power factor based on what type of load we have connected. Based on that, it is going to be. Yes. So in order to represent all these parameters, like sending end and receiving end parameters, we need to draw the phasor diagram representation normally. So that is why by taking VR as reference, if you see the graph, by taking VR as reference, to reach Vs, to reach the sending end voltage, there are two drops are there. One is IR, other one is IXL drop. Where IR is the resistive drop. Is is equal to IR is equal to I, we assume. So that is there. Wherever the current is there, this current is always lagged by an angle of IR because most of the time the load which is connected to the transmission line is inductive in nature. That's why. So pi r is there. With respect to this, exactly in parallel with this, you have to draw one line called IR. Since always the current is in phase with the resistance, that is why it is in phase. And from here 90 degree, you will draw IXL. That is another drop due to inductive reactance. In total, the drop is IZ. If you add this receiving voltage with respect to these two drops, that is the sending end voltage. Okay. So that is IZ. Since we take VR as reference, it is VR plus J0. The current is always lagged by an angle of pi r. That is why I is I minus pi r, which is I into cos pi r minus J sin pi r. Z is the total impedance of the transmission line, which is R plus JXL. And Vs, VR plus I into Z will be Vs value. That's the vectorial addition of VR plus I into Z. So using this, you can able to find the value of Vs. So VR is already known or determined, or we fix the value of VR. With that, we can able to find the regulation, efficiency, or whatever thing you want to calculate. You can do that. Calculations. But actually, the system is a three-phase system. How to model that in the three-phase way? You can see that there are normally the transformer is of star connection. Then here the load is also, we assume it to be a star connection. So there is a three lines are there, R and XL, RXL, RXL are the three transmission lines which is connecting the sending end to the receiving end. Sending end may be the transformer, receiving end may be your load. In that way, the single line diagram of that is also shown. Once again, voltage regulation. Then after that, how to find the power. Since it's a single phase, we assume that the three-phase balance system is modeled as a single phase system. To find the power, that is the receiving end power, it is VR, IR, cos pi r. Here IR is equal to IS, that's why we return it as I. So I is P by VR cos pi r, and this P is the receiving end power. Okay. So like this, you can find the sending end power also. So two powers are known, or otherwise I can say that the output power is known, the losses is also calculated, you can easily find the efficiency of the line. Coming to the medium transmission line. In medium transmission line, already we discussed that the model is for the line length between 50 to 150 kilometer and the voltage between the range of 20 to 100 kV. So here all the three parameters are considered, resistance, inductance and capacitance are considered. All three parameters are lumped parameters, and There are three models. In medium transmission line itself, there are three possible models are available in the literature. One is the medium transmission, N condenser method, nominal T method, and nominal pi method. These are the three methods which we have. Now there is N condenser method, nominal T, and nominal pi method. Why it is N condenser method? The entire capacitance are considered at the end of the transmission line, or otherwise receiving end of the transmission line. That is why it is called as N condenser method. The second model is called nominal T model. If you see the equivalent circuit of the model, it is looking like T. That is why it is called nominal T model. Pi, once again, it is looking like a pi structure. That's why it is called as a pi model. Generally, in practice, in the transmission line, if you model, we use nominal pi model only. The reason is, in pi model, the entire capacitance is divided into one at the sending end, other end at the receiving end. That is why we go for nominal pi model. Okay. So we'll see one by one. Yeah, in N condenser method, as we discussed, resistance, inductive reactance, and capacitance, all the three are lumped in nature. The capacitance is at the end of the line, transmission line, so that is near to the load it is. Okay. So lumped parameters are X and C. If you see the sending end current, I is represents sending end current, IR represents the receiving end current, there is a capacitive current. The sending end current, there are two equations you have to write, one is for the voltage, other one is for the current. So the current equation is 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 equal to IR plus IC. The total current equation, sending end current is equal to IR plus IC, and VS is equal to, the total voltage is VS, is equal to VR, that is VR plus whatever be the drop in this corresponding R and XL, we can find the VS value. Ultimately, in all these models, our aim is to find the regulation and efficiency in place. Okay, then condenser method. Here, once again, to draw the relation in terms of phasor diagram, you can see that similar to the previous case, short transmission line. Here also we consider VR as a reference. There are two currents, even three currents are there. The summation of IR plus IC. IR is the receiving end current, IC is the capacitance, shunt branch current. If you add these two, that is your IS. While drawing this, how to draw these current vectors in the sense? By taking VR as a reference, IR is lag by angle of IR. IR is lag by angle of IR. From here, the capacitive current is exactly 90 degrees from that. If you add these two, that is your sending end current. Okay? And the drop after VR, VR is there. If you see the phasor diagram here, VR is the voltage, the receiving end. The current which is flowing in this R and XL is IS. So that is why you can see that in parallel with IS, what you have to do is you have to draw ISR and ISX, ISXL.